Hey guys, can you hear me okay?
Yeah, we can hear you.
Okay, great. Thanks, Jacob. My camera, I updated my operating system on my Mac, and now my camera doesn't work anymore, so I'll have to fix that later. Interesting. Okay, guys, let's get started here. Let's see. So first, I was going to talk about project one a little bit. Maybe some of the questions or issues that some of you had run into. So the first thing is that this is a older type, what's called an NMOS process, because there's no PMOS FETs in this. So this is M1, this is also grounded. This is M2, let's call it. This is 1.8 volt. This is VN, this is V out. Okay, so it turns out that basically if we did a sweep of V in versus V out, we're never going to get to 1.8 volt or 0 on our outputs with our VN being in those values. So what happens? Well, when VN is 1.8 volts, say, oops, let me just put a different color. When VN is at 1.8 volts, okay, this guy's on, but this guy remains on. So this bottom guy is going to try to pull this output low, but this guy is still going to be on and trying to pull it high. So if you've it, so basically you'll never quite get to zero. You'll get to some value. Depends on, you know, what the ratio of this resistance to this resistance is at this particular point when Vn is 1.8, but you're never going to quite get to zero. Okay. And if you are looking in the case where Vn is equal to, whoops, is equal to 0. So over here, this guy's off, but this guy always is going to be limiting. It's going to turn off as soon as this V output goes to a threshold voltage below the supply voltage or below the gate voltage. Okay, so this guy is always going to be at, like, the highest it'll go is I don't know, maybe it depends on how you design it, right? Maybe 1.4 volts, maybe 1.5 volts. And in between, it's gonna, you know, again, depending on how you design it, it's gonna do something funky, ugly like that. Okay, and you can try to play with this, get a little bit higher, get this a little bit lower. You can try to get this a little sharper, but you're never gonna get to the full supply or ground. So remember, this is like, as sort of teaching you guys about enjoying the CMOS inverter when we get into it in detail, and some of the shortcomings of what happens if we don't have a CMOS type of logic. Okay, so that's the sweeping of the DC sweep. So this is, I think, is problem 1. Any questions about that? No? Okay. So then the second part of the thing is basically delay. So this is sort of problem 1. This is transfer function.
So I actually have a question, Professor.
Sure, go ahead.
So for part one, you said just play around with the parameters. Like, what's the final outcome you are you expecting?
Well, so, and this is, so 1 and 2 and 3 are kind of related together. Okay. So if your only job was to design this inverter as 1, and I'm not going to, like, penalize you guys for not optimizing across all 3 questions. So you won't be penalized, but the idea is that you'll kind of see that decisions in one thing will affect the other. So if you were just purely going to try to do part 1, what you would try to do is maximize your noise margin. Okay, so meaning that you would want to try to get this as high as possible, this as low as possible, and you'd want to get this kind of a short. So basically, you'd like to get as close to this as possible. Okay, that would give you the best noise margin performance that you could possibly
Got it.
achieve with this inverter. Okay, but I'm not looking for one answer. I'm, like, looking for you guys. Like, imagine, I'd like you guys to think about if you were assigned to do this task working someplace that did want you to do some optimization, but they wouldn't want you to spend 6 months trying to do this. So just sort of like, you know, get it to some level, try to get to a decent noise margin, as good as you can. Does that help?
Yes, thank you.
Okay, so next section is, and this is how you guys will see that, again, over and over again, the transfer function and transient and power consumption all affect each other. So the second one is about sort of delay or speed, or however you guys were going to look at it. And there, what we want to do, the setup is, you'll have this inverter, whatever you design here, you're going to basically put it here, and then you're going to put an input here, and then you're going to drive another 4 inverters like itself. Whoops. You guys get it? Okay. So then you want to basically look at the delay from this V in to this V out. Okay. So the question is that several of you asked is, what the heck then what am I doing with all this stuff? Why do I have these? And the answer is, again, so you're being asked to design this inverter for either you want to use it somewhere in your circuit, in your chip design, or somebody else is going to use it. And at no point is this logic gate going to be sitting by itself, driving nothing. Okay, there's just like, there'd be no reason to have it in your circuit if it's just sitting in space with an open output. Okay, so it wouldn't make sense to look at the delay of this without anything loading down this output. Okay, so when you simulate it, it makes sense for it to be simulated with a quote unquote typical load. Okay, some typical loading, because that'll give you some indication of how it might work in a real circuit when you actually use it. So then the question becomes, well, what is the typical, like, what should I use for this loading? I guess you could use a pure ideal capacitor, I guess. Sometimes you do use a capacitor in a real circuit. You're driving a capacitor. Okay, fine. You could use, other types of gates that you've designed. I don't know, like a smorgasbord of gates, whatever. You could put random stuff. But then the thing is, then every time you give your results, you have to explain in detail what you're driving. You'd have to say, I'm driving an ideal capacitor with 10 femtofarad load, etc. Or you could say, oh, I'm driving a NAND gate, and the NAND gate's input is this and that, whatever. So instead, what your ancestors decided to do is created this situation called fan out of 4. So FO4, or fan out of 4. So, when you talk about this to other designers, they know that the loading, all they have to do is know your circuit, because when you gave your delay numbers with this fan out of 4, it means you're driving another 4 elements like itself, and it's sort of like shorthand. So this is just a typical way to say, this is how I loaded it. Okay. And the reason, besides like this thing, that you don't sit there and do the simulation unloaded, is you could actually really fool yourself here. Okay. Let me tell you how. Let's say in an effort to get this transfer function to get this as idealized as possible in DC. Let's say for that, what you did is you made the load be very weak. No, wrong weak. Very weak. Somehow you decided that was the way to get the best noise margin, etc. Now, when this guy tries to drive, and you made this very strong, right? Let's say you made this very wide, very strong. Practically speaking means that this has a large W, this guy, W large, length small. In total, this means area of gate large. Okay, very weak means length large, width small. Okay, so if you did this and you had no load, if you were just simulating, putting a some kind of square wave here and looking at the output here, everything might look okay. But as soon as you load this down with yourself, with a device like yourself, all of a sudden you have a case where it exposes the weakness of the circuit, because when you're pulling this node down, it's okay. Like, remember, you'll have 4 guys like yourself driving 4 things like yourself. And this is also true in the case of CMOS gates. Okay, so 4 guys. Okay, so when you're pulling this node down, okay, things are probably okay. These are large devices you're driving, so as you'll see, these capacitors are going to be large, but your resistance is low. So okay, you'll drive them down pretty fast, reasonable speed. Okay, but when this is trying to be like a rise time or high going transition, now you got these really big capacitors because you created them. Remember, you made this a very big device to get your resistance low. So these are big loads. But remember, when you're pulling up, this is off. So you had this really high resistance or really this weak load, now trying to pull up these capacitors, these high value capacitors, and your rise time is really bad. So it'll make you realize that there's an optimization that you have to do between your transfer function and your delay, that you can't just focus on one or the other, because again, you have to have, in the end, you need a usable inverter to build something else with it. Remember that we're building these where we are in the hierarchy of things, where this might be your cell phone chip. Okay, so this might be your application software. We come down. This will be the the hardware description language. This will be the like the AL, arithmetic logic unit or whatever. This will be our circuits, okay? And this will be like actual, fabrication, like transistor level stuff. So we're designing stuff here. In reality, when you're doing stuff like you're doing in this class, you're down here and you're designing these circuit elements. So either you or somebody else can use it in these circuit blocks. So they have to be usable, both, have good noise margins, and they have to have a reasonable operating speed, whatever it is. And a lot of times you have to look at both to make sure you didn't take a wrong direction somewhere. So in part 3, I don't know if you guys have tackled that or not. You'll be asked to look at, this is the current through this device, okay, across a couple of high and low going cycles. This is why I suggested you make this VDD2 in your simulation, make this VDD1 or whatever, so that you can just tap this current and multiply by the supply, by VDD, and you just have the power, just I times power that's instantaneous power is going to look like that, which is the current at any given time. And sort of the average power is, let's say if you did across one cycle of high and low, it would look like that. Something like that. Okay. Then you'll see that also if you try to make these devices really powerful, then you might end up with like a huge power consumption issue. You won't be able to squeeze a lot of devices into a chip. And again, this will be true in a CMOS logic process as well. But so that's sort of what we're doing in the project. Any questions on those 3 pieces? Okay, so another thing, I just this is what I see sort of like a lot in simulations, but be careful of doing stuff like this. sometimes this is just a random piece of simulation advice. So make sure you connect all the substrate contacts. Okay, if you're using these models with substrate contacts, make sure the ends are all grounded. The P's could sometimes, as you'll see, that it could be hooked up to their own source or hooked up to the supply voltage, but just make sure you're connected. And then make sure that if you have, like, you don't do, unless you're doing it sort of very intentionally, don't do stuff like short outputs of different gates together. Okay, I see this all the time too. So remember that that's a very dangerous, like we have basically kind of at a high level, we have three types of devices in CMOS, okay? We have things like, inverters, NAND gates, NOR gates. Okay, oh man, I'm really screwing this up. Okay. Pull down. So they kind of look like that. Then we have, transmission gates that look like that. And then we have, like tri-state. We talked a little bit about tri-state outputs that look like that you could drive, buses, but you can basically disable the output. Okay. But so remember, unless you are in this situation or this situation, unless you're in this or in this, so whenever you have this, remember that always in the case of CMOS, either this guy's on or this guy's on. And you aren't supposed to have both of them on at the same time, but always one of them is on. One of them is guaranteed to be on. So if I had another gate that I drew, so pull up and pull down, and I shorted these outputs together, I could run into some serious problems because there's nothing that says that this pull down for this other gate won't be on at the same time as the pull up on this gate, which is, I immediately got a serious problem because it's like gives your output an unknown voltage. Plus then the pull down for this gate is fighting with the pull up for this gate, and you don't even know what, you might get beyond a degraded value. You just don't know what you're going to get here. Okay, so you do not want to short outputs together. Again, here you might short, you would put another pass transistor is another issue, because like as we saw in a multiplexer, so this would be kind of a mux, so this would be N1, N2 kind of thing. Or here we were talking about having multiple of these driving a bus. So it's okay in these specialized cases, but most of the time you'll be dealing with sort of inverters, NAND gates, regular static CMOS gates, and you never want to short those outputs together. So that's like if you see that yourself doing that, it's a definite no. Okay, of course on the input, so this would be on the input side, that's perfectly fine because you could have something driving both of these together, but this you never do this. It might, I mean, never say never, like driving some weird output buffer, you might want to do that. Well, we might see that or might not, but it'll be like 1 in a million times that you'll be doing stuff. So beware whenever you see stuff, teach yourself whenever you see stuff like this in this class where the outputs are short together, don't do it. Don't do it. It'll give you some really weird results. Okay. Any questions? No? Okay, guys. So I'll then move on to the rest of the lecture here. So in the, so I guess I already mentioned this here. So we worked our way through we're sort of doing the sort of introduction to CMOS logic. We talked about things like, inverters, NAND gates, NOR gates that have this pull up, pull down structure with N MOSFETs on the bottom and P MOSFETs on top. And we saw how you would, do complex gates or, create those with some combination of NMOS and P MOSFETs hooked up in series and how the pull up and pull down related with each other. Okay. And then we looked at sometimes you would want to use a transmission gate for things like multiplexers, some specialty needs. And then again, we would, again, you would want to have a tri-state buffer for specialty needs as well. Okay, so that's where they left us. And all of these are called, so far, they are called combinational circuits. Okay, what does that mean? Well, it means that at any point in time, the output is a function of, it's a combination of the inputs to this gate. And what it means is that this gate or this logic circuit has no memory of what happened before. So, for example, let's take the case of I don't know how many of you guys computer engineers, how many are not, but let's say take the case of like a finite state machine. And so let's just think of it as like a vending machine, okay? So if you had, in the case of a vending machine, you put in your money in first, okay? Then the vending machine decides, okay, the money came in, so it puts itself in a state where it's waiting for a button to get pushed. Okay, then you push the button and then it uses that button push to figure out, say, dropping you a Diet Coke or Coke or whatever. And then it decides that it dropped it, and then it puts itself back into a state where it's waiting for more money. Okay, so it's a finite state machine. So for example, when it's in the state waiting for the button to be pushed, this thing has to remember that in a previous time it got some money into it. Okay, if it was a combinational type of circuit element, it wouldn't know that because you gave it the money and now the money's not on the input anymore, and it can't remember that it got money. It just doesn't remember what happened in a previous cycle. So if you want a finite state machine, or as we'll see, if you're doing sort of pipelining, etc., you need another class of circuit that has a concept of time. And those are called sequential circuits. And broadly speaking, sequential means that, that there's some sequence of events that kind of happens, and the output is not just dependent on the input, but also on some event that might have happened earlier. Okay. And these are, ends up being latches, sort of two main classes of these, or maybe the entire classes, latches and flip-flops. Just for the sake of my knowledge or whatever, has anybody here not seen latches or flip-flops or doesn't know what they are? Everybody's seen them? Okay, great.
Yep.
Okay. So let's talk about a latch first. And so latches are easy to analyze. I'll actually grab my notes to make sure I'm not missing anything I want to say. Just one second, guys, sorry. Okay. All right. Okay, so what's latch? A latch is, again, it's just like a simpler element than a flip-flop. And what it does is when the clock is high, let's start with when the clock is low. So this is the clock to the latch, and this is the input to the latch. The Q is the output. Okay, input, output, clock. When the clock is low, the input could be doing anything. Notice here, D's going from low to high, clock is low, but so Q, the output doesn't do anything, because as long as the clock is low, the latch is, it's called opaque, I guess. Nothing goes from the input to the output. As soon as the clock becomes high, so anytime here, as soon as that happens, the output starts following the input. There's some delay. So notice the clock gets high here, and it takes a while for this output to go, sorry, from this input to go to the output. Okay, a little bit of time. And then when the output takes a transition while this clock is high, if the output makes a transition, the input makes a transition, the output will also make a transition a certain amount of time later. But basically, whenever the clock is high, the output follows the input. Okay, whenever the clock is low, the input can do whatever it wants, and the output will just keep its last value that it had when the clock was high. Okay, so this is the thing to remember, is its latch is level sensitive, clock level sensitive. Okay, and the way you sort of there's a bunch of different latch designs in CMOS, but this is one of the more robust ones, let's say, more complicated ones. So the way you would design it is you would basically, one way to look at it is you could have a multiplexer on the input, and let's say the clock is high. Okay, the D value gets multiplexed out. Here we have both the Q, the output, and the output bar. So latches, flip-flops, you see that's pretty typical. You have both the true and the negative sort of output available. So anyway, when clock is high, the output goes here. Okay, when the clock goes low, so you select here, what happens is you get two back-to-back inverters feeding each other. Okay, so let's see what does that do. So it's like we have this kind of situation. Okay, when clock is low. So let's say this was a 0 as an inverter. This would be a 1. And then this inverter would make this also a 0. So it's like a positive feedback situation. So it retains whatever value it had before it gets into this positive feedback loop, which just retains its value. So it'd be vice versa too. If this was a 1, this would be a 0, and this inverter would reinforce this 1, and the positive feedback loop would just sort of retain the value it had before. Okay, and the way you'd actually make that is so this is a multiplexer with transmission gates. This transmission gates gets clock on an NMOS, clock bar on the PMOS. This guy gets clock on the PMOS, clock bar on the NMOS. So it's basically like as if the clock was enabling this path, clock high was enabling this path, and clock low was enabling this path. Okay. And indeed, the way it works is if clock is high, the D basically goes, this guy's cut off, so you don't have a positive feedback situation. Okay, so this is just open. So D just sees this inverter to the output or the Q. So as in that case, when clock is high, anything that the D is on D, the inverted version happens on Q. So here Q was happened to have been low before. So as soon as clock goes high after a certain delay, it's goes follows D. Okay, and when clock is again high here, D goes down, Q goes down. It's as if you had well, this is Q here, the positive input, and then Q bar would be doing the inversion. Just be following it. Okay. Now, when the clock goes low, which is here or here, basically D is cut off, and you have this positive feedback loop set up. So if when clock goes low here, the D was low, so Q is low, Q bar is high. Okay, and then this guy reinforces the low here. So basically you're keeping a low on Q and a high on Q bar. And it just as long as you could, as long as you apply power to this chip, as long as the chip is on and it doesn't get clocked again, it will keep that value. It will keep that last value that D had. And then D, no matter what D does now, when clock is low, it's just cut off. You don't see it. Okay, on the output. Okay, any questions about the latch operation? We're going to go into more details about this a little bit later, but this is sort of like the intro to it. Okay, so a flip-flop is another sequential circuits, but it's edge sensitive. That means in this case, it's clock rising edge sensitive. So it means that the only time the output reacts to the input is when you get a, so whatever is the rising edge, whatever is happening on the input, on the rising of this edge of this clock gets reflected to the output. So the input can be going low or doing something like that, can be transitioning when the clock is high. When the input, sorry, when clock is high, the input could be transitioning and the output's not going to see it because it only sees transitions on the rising edge, or it could be the falling edge, but in this case, it's rising edge. So again, here, the clock is low, so the clock is high, transitions, nothing happens. Clock is low, input transition, nothing happens. As soon as the clock goes to a rising transition, though, the output changes. Notice here, the input changed a while back, but the output doesn't react until a while later when the clock goes through a rising edge. Okay, so so this is a flip flop. So now flip flops, I think I can make a general statement. Certainly, from a circuit standpoint, they're more complicated than latches. And as you'll see, that means more area, more power consumption, lots of things. But it's also considered a lot safer than a latch. What do I mean by safe? Oh, I'm sorry. Flip flop, I can also say, so let me make this 3. So remember this one because this is like easy one to get wrong. So i.e. it's easy to use a latch, and especially the like a, have any of you guys used Verilog or VHDL or anything like that?
Yeah.
Okay, so it's really easy when you're writing code to end up with like latches, and that could be very dangerous. Okay, because so anyway, let me talk about before that. So Flip-flops are more complicated than latches, and they are, in general, I could say they're slower. There's more delay through a flip-flop than a latch. So why ever use a flip-flop? Well, what happens is latches, because they're level sensitive, you could get a situation where if you are not extremely careful, you might end up, you have this whole amount of time where the input might unintentionally change, something else might happen in your combinational circuit, and that'll show up on your output. And it could be like a disastrous scenario. And remember that when you're actually designing a chip, you're not dealing with, 5 latches, 10 latches. You're dealing with, hundreds of thousands of latches, maybe millions and millions of latches, or flip-flops. Okay, you could be dealing with millions and millions of sequential circuits. So if you want to be as safe as possible. Okay. Now, having this sequential element, the flip flop, being edge triggered, it means that it's a lot easier, it's a lot safer to make sure that, because you only have to keep track of what its input's doing a little bit before and a little bit after your rising or falling edge, whichever edge you're on. You don't have to worry about what it's doing over the whole clock phase. Okay, so that's one. Two, your simulation tools and sort of timing tools. So the big part, as we'll see later, of doing chip design is a set of computer-aided design tools. That's a way to keep straight all these millions and billions of circuits, is you'll be simulating a big part of the chip in Verilog or HDL, some hardware description language, and then using synthesizers to synthesize the logic and then place and route it, etc. Those tools understand what to do with a flip-flop. They don't really know what to do correctly with a latch. Okay, so it really like confuses the heck out of them, and it's very, very dangerous. And it's very easy when you're writing hardware description language code to end up with latches when you synthesize your code. And that could be like very deadly for your design, especially if you're committing it. It's one thing to do it when you're doing a FPGA or something like that, a Xilinx part, and you can fix it. It's another thing when you're committing it to silicon. Okay. So typically the only place you'll see latches used is in very high speed data paths. So if you have, again, I don't know how many of you guys are familiar with like pipeline stages, etc. Sometimes you're just trying to go as fast as you possibly can, but it's a very small part of the circuit. It's like very hand tuned. You're not using the CAD tools to meet timing requirements, etc. That's typically where you use latches, and you should try to avoid them anywhere else you can. So just remember this. If you don't remember anything else from this class, is use flip-flops as a rule, and only use latches when you know you want to use a latch. But do try to avoid them. I've seen a lot of problems with latches in my brief time. Okay, so that's a flip flop. So what is a flip flop? Well, it's actually ends up being 2 latches back to back. Okay, so this is the first latch, and this is the second latch. And what you do is you invert the clock of the first latch to the second latch. So we're going to look through this in a little bit of detail, but if one way to look at it is, first this input goes to here, then you sort of cut off this side, and then the output goes to the input of this side goes to the output. Okay, so that way you get this sort of edge. Only during the edge it looks like it's transmitting. So to look at it, so this first latch Remember, it's getting an inverted clock. Okay. So in this first latch, when the clock is 0, okay, in these areas, you basically get D goes to the Q sub M, okay, goes to here. But remember that the second latch gets clocked by the true clock. So when the clock is 0, its input is off. So basically D goes to here, but stays there. The output, the second latch, is in this positive feedback loop. So as long as this is 0, this is 0, this Q is the output of the second latch. So it's just sitting there. Oops. It's just sitting there. If it was 0 before, it'll stay 0. It doesn't care what D is doing. If it was high, again, it doesn't care what D is doing. It's keeping it's retaining the previous value it had. Okay. Now when clock goes from low to high, what happens is that D gets disabled from the input of this first latch, but this first latch is retaining the previous value that D had, and now it's able to go to the output. Okay, so when at that point D, whatever was in D before, now when you go from low to high, whatever value this D was before goes to the output. Okay, so that's what happens on the rising edge. Now, when clock stays high though, D, because it's cut off here, it could do all sorts of stuff here, is still not going to transition to the output because it's cut off here. Okay, and you just keep the previous value of D until this sort of sequence from low to high happens, in which case you make the transition and then you make the transition to the output. Okay, any questions about that? We're going to get a lot more into timing when we get to clocking and stuff, sequential circuits. Okay, so this bears repeating. In flip-flops, there are, you can get bad events happening. There's two types of bad events. One of them is that if you had a flip-flop and then you had some combinational circuit. So this could be a jillion logic elements doing whatever logic elements do. Okay, so this is combinational, a cloud of combinational circuits. Going to the next layer of flip-flops. This is how it typically works, is basically you end up storing a previous value, making a transition to the next one in one clock cycle. Okay, so you could have a situation where this delay ends up being bigger than you'd hoped for. Okay, this delay ends up being bigger than you hoped for, and so the data does not make it from here to here in one clock cycle. Okay, it gets up to here. I don't know however we want to look at it in one clock cycle. Okay, so you get the incorrect answer on the output. That's called, as you'll see, that's called a setup violation. I guess familiar with setup violations? Heard about setup violations?
I don't think so, no.
No. Okay. Well,
No.
if you go into this any FPGA or chip design, you'll hear plenty of it. Setup and hold violations. Let's call it setup violation. It's not a good violation, okay? Which basically, it's not good because this delay is longer than you expected, but it's not the end of the world. I mean, what happens is you'll have to reduce your clock speed at some lower clock speed, okay? So some longer clock period, this clock period be long enough for the logic to make it all the way, and then your chip will work. Okay, so let's say you design this chip for a 2 gigahertz clock. You got a setup violation. You reduce the clock to 1.8 gigahertz, and your chip starts working because now, whatever path was too slow now has enough time to make it to the next layer of sequential circuits. Okay, not good because, your chip's supposed to work at 2 gigahertz. But, in practice, what you do is if your chip's supposed to work at 2 gigahertz, you might design it for 2.2 gigahertz or something, give yourself some margin. Okay, whatever. But at least you got a working chip either way. Okay, so the other thing that can happen, which is absolutely catastrophic. So this is not this. I would say the setup is not good, but not catastrophic. But this situation where you have a flip-flop and not much delay and another flip-flop. Okay. So what happens is, and so when you are routing your clock, delays, etc., it's not guaranteed that this clock here and this clock here, they might be millimeters apart, who knows, or whatever. Depending on your clocking, you'll see that even circuits that are sitting right next to each other can have a clock that might be delayed, as you'll see, like because you have lots of issues with clock distribution. It's a big part of the chip design. So what happens is, if somehow this output races all the way to this input on the same clock edge, let's say you even didn't have any logic, let's say you had a flip-flop. So you have this kind of situation sometimes when you have scan chains or something. I won't go into those, right? But anyway, some test parameters, you just have flip-flops like chained together and you're shifting data across, right? Or let's say you have a shift register, for example, okay? So if you're not careful, what happens is this on the same clock edge, this guy can get here too quickly and then race straight through. Okay, that's called a hold violation. Okay, and that's absolute death. Okay, because it doesn't matter what you do to your clock. It doesn't matter you slow it down, speed it up. It doesn't matter. It's racing through on the same clock edge. So no matter what happens, it's going to race through because it's edge. Remember, it's edge triggered. So it doesn't matter what you do. These edges, you just have edges, and that's showing up at kind of the same time, no matter when the next, the falling edge of the clock is, doesn't matter. It'll just race through and you get this hold violation. So your chip will plain old not work at any clock frequency, and like there's no way even to debug it. A lot of times, one of the first things you do when your design comes back and it's got some problems, I mean, this is absolutely one of the first things you do, is you slow the chip down. Okay, whether you're designing an analog chip or digital chip, what you do is you cut the clock rate in half and see if you can get it working at some clock rate. Usually you can get it working at some clock rate. And then from there, once you have something that's alive, it's working, it's doing something recognizable, now you can start debugging why it wasn't working at the full clock rate. At least you have something that's responding to you. Okay. If you have a chip that comes back and doesn't work at any clock rate, you won't, besides it being catastrophic, doesn't work, you have to redo the silicon. Remember how much it costs to fabricate silicon. Besides that, you really have no good way to debug it either, because you don't have, at no clock frequency can you get this thing to function. So you don't even have a point to start debugging anything. You really are, just DOA and it's not going to wake up. And again, imagine if you have something wrong in a very large chip at some small location. that's going to be propagating in all sorts of weird ways into the rest of the chip. And it's going to be very, very difficult to debug what's going on with that chip. Okay, so anyway, so hold violations are really, really bad. Again, if you just, maybe the second thing to remember from this class, setup violations are not good, but at least you can have a working chip. Okay, so the book says, I'm not sure what we're gonna do, but one way to completely avoid hold violations is, instead of distributing one clock, so let me just do this. So if you had, let's say this is, I do this right, I can't get this right. Okay. So this is my clock. So one thing you can do is, instead of using this as your clock, you could have a two-phase clock. So clock, let's say clock 1 looks like this. And clock 2 looks like this. So what you would do is you would, this would clock your all the flip-flops first latches. So in this case, you see it's getting phi 2 or phi 1. Oh, okay, second latches, just to be in sync with this drawing. So second latches. And clock 2 would be clocking all the first latches of all the flip-flops. Okay, that way, if you end up with a hold violation, you can, and if you've made this outside the chip, you can actually separate these edges from each other, okay, independently, basically to make sure that you don't get into this hold violation. Okay, so this is a very safe approach. It's also not something that's really used in the industry, I would say, okay, because it's also you can't go very fast. So in the industry, like it says here, there's a lot of work on handling the skew of your clock network. And again, we'll see this later, to basically make sure that you don't end up with this hold violation. And you can imagine it's a big, big deal. I sat through a very interesting, right now, just this week, there's a conference called the Solid State Circuits Conference. That's the main, chip design conference of the year. And so I'm attending that virtually. Thankfully, that's one of the good parts about COVID is you don't have to go anywhere to attend the conference. But there was a whole 3-hour presentation from IBM on clock distribution, and a big part of it was, I would say, it was all of it almost was skew management. Okay, to make sure you can run stuff at very, very high clock rates and don't run into problems like hold time violations. Okay, so that's all we're going to talk about sequential circuits right now. We're going to come back to these in detail later. And by the way, like a very, very big part of chip design, when you're designing a chip, we're going to be spending a lot of time on combinational circuits, analyzing their timing, optimizing their noise margin, so on and so forth. Thinking about how we can reduce their size so we can pack all of them in there. But in actual chip design, the majority, as important as the combinational circuits are, and you get the right functionality, et cetera, but majority of your time and the majority of your problems in chip design are with the sequential circuits and clocking. It's like much bigger issue than like anything else. So it's all about timing, clocking, clock distribution. That's like a huge thing that that's usually what delays your schedules because you're having a hard time um, creating a system clock that'll work without causing all these problems. So anyway, the timing, if you go into this business, whether you're doing FPGA design or chip design, like clocking is going to be a big part of your life. Okay. So having said that, now we're going to talk about, we talked in the previous set of slides about layout and layout rules. And, I think I got a homework assigned to you guys to do, do layout, sort of at least on paper. But unfortunately, we still don't have access to the CAD tools that we need to do the layout. We only have at the moment access to Spice to do simulations on. So I'm still trying to figure out what to do with this. I'll just talk about it a little bit. And I think what we're going to end up doing is like a project where you have to read a layout and simulate it. And I'll give you guys an example here. Okay. So having said that, let's rewind here. So we've got our combinational gates, we got our sequential gates, and now you want to create a layout that represents those gates. Okay, so layout, as it says, it can take a long time, especially a long time to optimize it. So what you typically do is and same with circuit design, right? Takes you a while by the time, as you've seen in project one, you're designing one inverter. First, you're doing the noise margin with a DC transfer. Then you're doing some timing simulations, and you've got to look at the power consumption. So every logic element you design, it takes a lot to optimize. Okay, so you don't want to do this over and over again for a chip that has multi-million gates. Okay, so what you typically do is you create a library of parts. What does that library look like? Well, it'll have an inverter that you can reuse over and over again. Now, because you have a lot of different cases where you might want to use inverters. The inverter might have a large fan out. It might have a small fan out. It might need to be a fast inverter. It doesn't need to be a fast inverter, so it could be low power. So you might have a bunch of different flavors and inverters you do, different sizes, right? So it'll be sort of a nominal inverter. And let's say it'll be a fast inverter, means it'll be big. So that you can drive big capacitive loads. Might do a low power inverter. So it'd be like maybe 4, 5, 6 different flavors of inverters. The circuit, they all, CMOS inverter always looks like this, but the sizes of P and N would be different on these. But anyway, in your library, you'll have 4 or 5, and whenever in your design you need to use an inverter, you just pick one of these. You don't go and design one from scratch because it's time consuming. Same thing with NAND gates. Like, let's say you might have, I don't know, like a couple of different flavors of NAND gates. Again, use those a lot. You might have, whoops, I drew a NOR gate there. Sorry, guys. NAND gate. So you might have a 2-input NAND gate. You might have a 3-input NAND gate. As you'll see later, you probably don't want to get more than 4 inputs. So you might have sort of 3 NAND gates, NOR gates. You get the feeling. So you might have maybe, I don't know, somewhere between 15 and 50 parts in your library. You'll have, you know, a couple of latches, a couple of flip-flops, and basically use this whenever you're, you know, imagine if you're building a complex logic function, you're just pulling this, either you're doing it or your software is doing it. The synthesis software takes your hardware description language and turns into a circuit. It goes in looking in your library to see what to pick. And depending on how smart it is, it'll pick the best one and use it. Okay. So basically want to create a library and use the library. Okay. So, okay, that makes sense from a circuit standpoint. I think we can always, you know, get our heads around that. We just want to reuse these parts. Now, the issue is you'll also, in the actual mask fabrication, you also have to use the layouts from these different circuits. Okay. So you want to be thinking ahead so that it's easy to have these layouts talk to each other. For example, the weak N could be driving a strong N for whatever, sorry, the weak inverter could be driving a large inverter, etc. So if this thing looks like this and this thing looks like that, then like now you got to scratch your head, what do I do with this? So this is, sorry, this is the layouts. So this is, let's say this is the layout for this. This is a layout for that. Then you put your chip together, you got these empty spots here. Maybe your flip-flop looks like this, you know, this is driving some kind of a flip-flop. Again, you're gonna end up like now you got this sort of enigma on what to do with it. Just not a very, it could be a very inefficient way to, you know, when you're, especially when you're trying to reuse stuff. So the idea is that at the very beginning, this is called the standard cell methodology, is that you come up with some rules. So all of these different layouts from all of your different gates and flip-flops, etc., play well together. Okay, so how can you do that? So one thing is you say, okay, I will keep all the heights the same. So this would be a small inverter, and this would be layout. And a strong inverter would have the same height, but can have any width that's needed to, you know, have to use the bigger transistors. And a flip-flop has got a lot more stuff in it than either inverter. So again, it'll have the same height, but again, it'll have as much width as it needs. Okay, so you basically agree on with yourself or with other people that this is the height. Every single cell, so-called, in your library will have the same height on the layout. Okay, another thing you could do is you could have it so that all the VDD or the power lines line up with each other. So when you put these next to each other, all you have to do is to hook them up like this, and all the powers are connected together. And you could have them so all the grounds are on the bottom. So again, when you put these things together, it's easy to connect these things together. You could always have the inputs. Oops, shouldn't have done that. Could always have the could always have the input be down here, and the outputs pick a different color. Nope, it's not a different color. Up here. Okay, so it's easy to connect up from one layer to another. So you can always put the N MOSFETs on the bottom and the P MOSFETs on top. So again, as you'll see in the spacing, etc. So basically you end up with these kind of rules, and this is called the standard cell design methodology. And on 99.9999% of your chip, you'll have these things. You'll have these standard cells because you want to use stuff from your library over and over again. The only time you won't have these is in your fastest, let's say fastest pipelines that you're just honing and tuning every single transistor on those gates. You don't want to reuse anything because you're going very, very fast, or I don't know, that's about it, is when you would use hand laid out something that's not a standard cell methodology. So the standard cells are used all the time, and you want to tend to make your logic gate layouts in a standard cell so it'll be easy to um, lay out. So here's an example of what this kind of thing would look like. Again, notice we have ground. Let's say these were, well, anyway, this is grounds you have on the bottom, supply you have on top. We've got PMOS on top and NMOS on the bottom. Okay, so, and like here's a NAND gate. Notice that, so if I can get both of them here. Okay, if I look at this inverter and this NAND gate, notice that the grounds are on the bottom. So if this inverter was sitting next to this NAND gate, the grounds would hook up directly. They are the same height. Okay, so meaning that the inverter would just sit here. The width of the NAND gate is wider because I have to put in 1, 2, 3 gates. I have to hook that up. I have only one gate on the inverter. Here I have 3 NMOS, 3 PMOS gates. So this will want to be wider. Okay, so the height of this well is the same as this well. So the wells can all connect together. So you can kind of get an idea about how like the standard cell logic works. And then what happens is this maximum height, okay, is some, again, we talked about lambda based design rules. Depending on the rules is going to end up being some height, and like basically that's what you'll, but the widths can be anything. Okay, stick diagrams I'm not going to get into. I've really not really used them very much in industry. I asked my friends, nobody I know has used them. I'm sure they're useful. They're kind of like a shorthand way of trying to figure out your layouts without actually doing the layout, but I'd rather just do the layout. Don't know why would you do an intermediate. I know why, but I can't be bothered. Okay, so what do I want to say about wiring tracks? I'm not sure I want to say anything about wiring tracks without confusing you guys about these things. But so I think what we're going to do, and this is sort of heads up about project 2. So again, because it's difficult for you guys to do layout, what I'm going to do for project 2 is give you a few different layouts. And what you'll have to do is to read the layout and figure out, for example, this is pretty easy for me to see immediately, even if nobody told me it's a NAND gate. I can see that, this is the N MOSFETs. There's 3 of them in series. This is the P MOSFETs. I can see they're hooked up in parallel, and the output of the NMOS is hooked up to the PMOS. Anyway, I can see that this is a NAND gate. And then from this, I can see the width and the length of the NMOS transistors, the width and length of the PMOS transistors. I can figure out the drain source areas. Anyway, I can basically get a SPICE schematic reading this layout, then I can simulate it to see what it looks like. So I think that's what we're going to do for project 2. So basically start with the layout, read it, and create a schematic from it, and then simulate it, which is also something you'll end up doing a lot in the industry, because a lot of times you're looking at somebody else's layout. Usually you're working with a big team. you get some circuit, maybe it's not running as fast as you think it should or you need. So you want to see why. So you have to kind of create a schematic from the layout with all the parasitics and so on and try to simulate it. Okay, guys, so I think this is where we are with slide deck 4. And I'm going to stop here because, slide deck 5 is going to, taking, now we're done kind of with the intro to all the different aspects, and slide deck 5, we're going to start drilling down into the specifics of NMOS and PMOS transistors, and the current versus voltage characteristics and how they really work, and idiosyncrasies and third order effects and all that stuff. So I'm going to stop here and then we'll start with that on Thursday. Okay. Any questions? If not, have a good couple of days. I'll see you guys on Thursday. Take care.
Thank you, Professor.
Thanks. Bye.
Thank you, Professor. Have a good one.
Thank you. Bye.